welcome you all in this course of mechanical measurement systems. Today we will continue to discuss the flow measurement in engineering application, and we will start with the introduction and the type of flow meter. We will take different type of flow meters in this discussion. Regarding the introduction, I have already given you introduction of the flow meters, but here we will be using different principles of physics in order to measure the mass flow rate or volumetric flow rate. We will be using, for example, we will be using the Faraday's law for induced EMF. We will be using Coriolis component for the flow measurement. We will be using the principle of Hall effect. We will be using principles of vortices or or other principles of physics. We will start with the rotameter. Rotameter is again a obstruction type of flow meter. So, in a rotameter, which is normally used, I think in many of the industries, and it is used as a flow measuring device, not only industries, in the research labs and the research institutes also, and it is very popular. And the rotameter is very simple in construction. It has a tube, and tube does not have a constant cross section. Tube does not have a constant cross section. The cross section of the tube varies from bottom to top. Let us say it is like this. It has a bob. Bob has a specific geometry. And the fluid flows from the bottom. Rotameter can be installed in the when the pipe, the flow direction is vertical. On a horizontal pipe, it cannot be installed because we make use of the gravity force here. So, this bob is pushed by the water which is entering the flow meter, right? And as when the bob is at the bottommost position, there is no flow. There is a marked scale here. In no flow condition, it is at the bottom. When the fluid enters, so let us take water. Water is the working fluid. Water enters the flow meter, it pushes the bob, it goes up. When it goes up, from the sides of the bob, the water starts moving, right? It is further pushed. When it is further pushed, more space is available for the water flow, and bob remains suspended in the fluid, and we can take, if there is a marked scale here, from scale we can take the reading. But issue is, what is the physics behind this? Because how does it come into the equilibrium? And how the equilibrium is decided? As we keep on increasing the flow rate, the bob keep on shifting the position in vertical direction. For the highest flow rate, it will be somewhere here. Right. So, how the position of the bob is decided, and what are the force which act on this rotameter, that we will discuss here. Now, in this rotameter, there is a drag force which plays a major part. The drag force is created due to presence of this bob into the flow field. And this drag force, Fd, and the buoyancy force also works in this direction. Drag force will work in this direction. Buoyancy force will also work in this direction. So, buoyancy force is going to be the force equivalent to the mass or the gravity force or the mass of the fluid displaced by this bob. So, mass of the fluid means volume and density, volume of the bob and density of the fluid. Sorry, volume of the bob and density of the fluid, right? This is the mass of water replaced by this bob, right, multiplied by G. So, drag force and this is buoyancy force which is working on it, it is equivalent to the force or the mass or the weight of the water which is replaced by this bob, that is volume multiplied by density multiplied by G. Gravity force on the bob is volume of the bob, density of the bob and G. Now FD, how to calculate FD, drag force. So for drag force we have the formula FD is equal to CD, area of the bob, density of the fluid, mean velocity of the fluid square divided by 2. This is drag force. And this drag force is equal to VB G rho B minus rho F. So definitely the rotameter will not work in under space or in zero gravity, or if gravity is changed or in reduced gravity it will not function properly. In zero gravity it will not work at all because we are taking help of gravity force here for the purpose of measurement. So now here if you do the manipulation we will be getting UM square is equal to 2 VBG by CDAB, or we can say rho F, rho B by rho F minus 1. Because rho F we have taken here, so 2 VBG CDAB rho F rho B minus rho F minus 1. That is UM square. And if we take the under root of this UM, this then we will get mean velocity. Now once we have the mean velocity UM, then UM multiplied by the area will give the quantity of discharge Q. Here also this rho F will not be there. The UM is going to be the under root VBG by CDAB multiplied by the ratio of the density minus 1, right? And then once we have the value of UM, then we can multiply by A, then we will get the volumetric flow rate. Volumetric flow rate again multiplied by the density of the working fluid, that is water here, then we will get the mass flow rate. Now for area, because area is varying, this is variable area flow meter, the area is varying. So in order to find area, but area is varying linearly. Area is varying linearly, so A is equal to pi by 4 d plus AY. Now what is d plus AY? A is slope and Y is the distance. Slope is, suppose this is d2, so d2 minus d1 divided by L, right? And if we multiply by Y, we will be getting d plus AY, pi by 4 minus, this is, sorry, pi by 4 d square minus pi by 4 d1 or d square. So this is the area which is available for the flow. D is the diameter of the bob because it occupies certain cross section. So area available for the flow is the cross section area of the tube minus area occupied by the bob. So bob, the density of the bob has to be as high as possible, right? For the good, that is why it is made of only iron. We take iron bob, we don't take plastic bob. So bob, and it depends upon the other factors also, but in most of the flow meters you will find that the bob is made of iron. So there is a substantial difference between the density of the bob and the density of the working fluid. Now after this obstruction type of flow meter, we will be taking certain non-obstruction type of flow meter. For example, magnetic flow meter. Now in magnetic flow meter, the principle of electromagnetic induction is used. It does not have any moving part. First of all, it is a non-obstruction type of flow meter. It does not have any moving part in it. It has certain electronics which is used for the flow measurement. But the limitation of this flow meter is that it does not work with non-conductive fluids like distilled water. The flow of distilled water cannot be measured with the help of magnetic flow meter. Hydrocarbons are not electrically conductive. Flow of hydrocarbons cannot be measured with the help of magnetic flow meter. But if there is a normal water, because normal water has dissolved salts, right? So the flow of normal water can comfortably be measured with the help of this type of flow meter, and it works on the Faraday's law. So if the water is flowing, suppose there is a conductor, right? Perpendicular to it, there is a magnetic field. Suppose, and conductor is moving in this direction, and there is a magnetic field in this direction, perpendicular to it. On the third axis, the EMF will be induced. So if we are putting magnetic B from top to bottom, B, electromagnetic field. So perpendicular to this board, EMF will be generated. And this EMF will be proportional to the velocity of the water, velocity of the charged particle, right? And this EMF will be equal to B L and V. This EMF, induced EMF, will be equal to PL V. V is the velocity of water, B is the strength of the electromagnetic field, L is the length, right? Now here, so V is equal to E by BL. Once we have the value of V, then multiply by cross-section area. If you multiply this by cross-section area, you will be getting Q. And once the Q is with us, we can find the velocity of mass flow rate through electromagnetic flow meter, right? So it is the flow meter which is non-obstruction type, right? And this flow meter, the limitation of this flow meter is that it cannot be used for the non-conductive fluids like hydrocarbons and distilled water. If there are vibrations in the system installation, then also this type of flow meter is not used. A calming region has to be provided in this type of flow meter. It is approximately 15 D for upstream side and 5 D on downstream side. The flow meter has to remain fully flooded. There should not be something like it should not be a stratified flow. Now, to ensure anything to be fully flooded is a difficult thing, because we never know, because pipes are not transparent. So we never know whether it is fully flooded or not fully flooded. So on the downstream side, if it is possible, sometimes it is not possible. If a U-turn is provided like this, so for any flow rate, it will be ensured that the pipe is fully flooded. For ultra low flow rate, other issues will come. In that case also, this system may not work properly, because in that case some stale fluid may remain there. So this flow meter is suitable when the entire flow in the pipe is fully flooded and there is a full-fledged flow in the pipe. Calming section has to be provided on the upstream side and the downstream side. There has to be no vibrations. It can be used for slurries also. It can be used for the slurries also, because there is no obstruction, so there is no issue of choking. Now after this magnetic flow meter, there is another flow meter which is an obstruction type, that is turbine flow meter. Turbine flow meter. in turbine flow meter, in the passage, there is a turbine, there is a disc containing blades and vanes, right? Water, it's a sort of axial turbine. When the fluid flows over this turbine, it starts rotating. Higher the mass velocity or higher the velocity of the fluid, higher the RPM of the disc, right? And higher the RPM of the disc, so RPM of the disc can be related with the mass flow rate, or the frequency of the rotation can be related with the mass flow rate of the fluid. So there is a pickup here. There is a pickup here, proximity sensor. So proximity sensor senses the pulse which is coming to the proximity sensor, and this can also be used as a totalizer. If a particular time duration, if you count the number of pulses, that will give the total flow, and pulses per second will give you the mass flow rate per second or volumetric flow rate per second. So turbine flow rates are not very costly devices. The flow should not have any swirl. If it is a swirl flow, then first of all the pressure loss will be high, and the reading we are going to get will not be proper from turbine flow meter. Otherwise, cost wise, it is not very costly device, and it has some mechanical wear also, because a wheel is rotating on an axis. So it has certain mechanical wear also, but otherwise it is a very good device for the flow measurement. Now after turbine flow meter, we will take vortex flow meter, vortex shedding, principles of vortex shedding. Vortex. Vortex shedding. Now what is vortex shedding? Now suppose there is a bluff body. Bluff body, a cricket bat is a bluff body. A bluff body, this duster can be a bluff body in a flow. So when a bluff body is inserted or put in a flow, then on the trailing side of the bluff body, suppose this is a bluff body, on the trailing side of bluff body, eddies will be formed. So when a bluff body is placed in the flow, the vortices are formed on the downstream side or the other rear side of the bluff body. So suppose this is a bluff body, it's a flat, so a cricket bat is also a bluff body. So when the flow is coming from this direction, on the trailing side, vortices will be formed. Now these vortices can be counted with the pickups, with the help of the pickups. And if you are able to count these vortices, because number of these vortices is proportional to the velocity. So if we are able to count the frequency of these vortices, we can find the velocity of the fluid. And piezoelectric crystals are used. A sensor of piezoelectric crystal is used on the trailing side of the bluff body in order to measure the vortices, number of vortices. And there is a number, dimensionless number, straw hole number. So F is equal to SV by L. L is the characteristic length, V is the velocity, S is the straw hole number, and F is the frequency. So once we have the frequency with us, straw hole number with us, right? It is essentially a constant. This number is essentially a constant, and it is dependent on the body shape of the body in certain operating limits. So once we know the shape of the body, straw hole number is with us, characteristics length is there, frequency is there, we can always find the velocity. So vortex shedding or vortex flow meters are also available in market, and they are a little costlier than these type of turbine types of flow meters or electromagnetic flow meters. But these flow meters are quite reliable, and we can go for the low flow rate also, or we can measure the low flow rate also with the help of these flow meters. Second thing is conductivity is not an issue here. We can I mean, measure the flow rate of any kind of fluid, whether it is electrically conductive or electrically non-conductive. Now, after this vortex flow meter, there is another flow meter which is very popular, especially in the oil industries, that is ultrasonic flow meter. Now, ultrasonic flow meter works on the principle of Doppler's principle. It is based on the Doppler principle of frequency shift. You must have studied in physics the Doppler effect. When the source and receiver, there is a relative motion between source and the receiver, right? In that case, there is going to be a shift in the frequency by the receiver. If the receiver is stationary, source is moving in this direction or in this direction, the receiver will receive a different frequency which it has emitted. Suppose it has emitted frequency nu. So the receiver will receive nu dash, and the value of nu dash will depend whether it is moving away from the receiver or it is going towards the receiver. Now, same principle will be used here in the ultrasonic flow meter. First of all, it is a non-obstruction type of flow meter, and this flow meter can be used for the large diameter of the tubes, right? Especially in the oil industries, for the transportation of oil, large diameter of tubes are used. So here in ultrasonic flow meter, there is a emitter and receiver. There are two things. One is emitter and another is receiver. And they are put in the flow at a certain angle. Right? Now, ultrasonic waves are emitted and received here, and this is emitter, this is receiver, and this is emitter, and this is receiver. And flow is in this direction, right? So, the time difference, let us say this receiver receives in time t1, this receiver receives the time t2, right? Then 1 by t1 minus 1 by t2. Difference 1 by t1 minus 1 by t2 is going to be c. Suppose this is theta, right? So we will take the horizontal component of this, and this is going to be the c plus C plus this is V. So C plus V cos theta divided by L, whatever distance it is traveling, and then here it is going to be C minus V cos theta divided by L. Now theta is known to us, this is theta, right? And L is known to us. T1 and T2 we have calculated, just not calculated, we have just measured with the help of data acquisition system, right? And that we can always find the value of V. So in a ultrasonic flow meter, what is being done? On a pipeline, we have just put emitter and receiver at two places at a certain angle, right? So, and using this equation, we can, because these calculations are also done in the hardware itself. So simply you will get the flow display on the display screen, that this is the mass flow or this is the velocity of the flowing fluid, or if you multiply this by a diameter, you will, or the cross section area, you will be getting the volumetric discharge. Now after this ultrasonic flow meter, we will take up the Coriolis mass flow rate meter, which is very popular in industries. You see, it is very popular because the metering through this flow meter is very accurate. So it does the accurate measurement of mass flow rate, and it is quite costly also. It's a very costly flow meter. Uh, mass flow, Coriolis mass flow rate. So, Coriolis mass flow rate meter works on the Coriolis effect. Coriolis effect can be visualized. It you'll find in many places in nature. Even the direction of the ocean currents in the north hemisphere and the south hemisphere is decided by the Coriolis effect. In our day-to-day life, if you look at the flying aircraft, is the best example. When you see a flying aircraft, then aircraft, when it is taking either right turn or the left turn, either nose will go up or it will dip. It will not remain in the same plane. So when there is a motion in two axes, suppose in an aircraft, let us take example of aircraft. If you look from the rear from the aircraft, suppose the fan or the impeller is moving in the clockwise direction. It is moving in the clockwise direction. When it is moving in the clockwise direction, we will take this axis as this axis. So clockwise direction, this finger, index finger. Then it is moving, suppose it is moving left. So when it is going straight and moving left it is making a curve. It is making a curve in anti-clockwise direction. It is something like opening a bottle. So it will be represented by thumb. If these two things are there, precision will take along the third axis and couple will work. And couple will work by joining these two fingers. So when it is moving left, the couple will work like this. It means, suppose this is the aircraft, the couple will work like this. So nose will go up and the rear will go down. I just am repeating. If you are standing behind the aircraft or on the rear side of the aircraft and looking at the front, and if the impellers are moving in clockwise direction, then it will be indicated by this finger. This is how to find the Coriolis component. This is just how to find the Coriolis component. And when it is moving in the left, it is taking the left turn. When it is taking the left turn, then it is something like opening a bottle or counterclockwise movement. So it will be denoted by thumb. If you connect these two, and then the couple will work in this direction, it means the nose will go up and tail will go down. Suppose impeller is not moving in clockwise direction, it is moving in counterclockwise direction, then the couple will be like this. When the aircraft is turning left, then nose will dip and the rear will go up, something like that. Now how we can use this principle, precision in third axis, in Coriolis mass flow rate meter? In Coriolis mass flow rate meter, because first of all it is a mass flow rate meter. So we don't have to do the, in earlier flow meters, we were simply finding the value of Q and then we are multiplying it by A. Sorry, multiplying by the density. So, and sometimes velocity multiplied by area multiplied by density. Then we are finding the mass flow rate. But here in the Coriolis mass flow rate, we can straight away we can find the mass flow rate of the fluid. And the working principle is like this. If there is a tube and the fluid is flowing, there is a U tube, or let us take, there is a U tube, and fluid is flowing in this tube in a particular direction, let us say in this direction. Now I vibrate this tube perpendicular to this board. So this tube does the vibration. Suppose this is a U tube and it does the vibration. During vibrations, depending upon the direction of the tube will get twisted. And when tube comes in opposite direction, it will be twisted in another direction. So this twisting, if we can measure this twisting angle with proximity sensor somewhere here, then twisting is comfortably related with the mass flow rate in the fluid, because if there is no fluid flow in the tube, no twisting will take place. If the tube is empty, if you vibrate the tube, it will not twist. But the moment the fluid starts moving in the tube due to Coriolis component, the tube starts twisting. And if we take two tubes together, this signal will be amplified. Instead of the flow meter, it is done. Instead of taking 2 tubes, they have taken 2 tubes so that this is amplified, the twisting is amplified. And this phenomena is used for the mass flow rate, this Coriolis mass flow rate meter. And in this flow rate meter, it is also used for two-phase flow as well. In the two-phase flow, suppose I have to measure the mass flow rate of foam. Foam is a mixture of gas and the liquid, right? Homogeneous mixture of gas and liquid. For that purpose, this is the best flow meter which can be used for that purpose. So the beauty of this flow meter is it is used for the mass flow rate. It doesn't matter whether it is a liquid phase or the solid phase. But normally, when the liquid phase is more than 10% or 20%, this flow meter has to be recalibrated. So we have to have calibration curves for different fractions of liquid and vapor if you want to have correct measurement of the flow through this flow meter. Now, another one is the Hall effect flow meter. Hall effect flow meter. Now, in Hall effect, suppose there is a conductor, and I should explain you first the Hall effect. There is a conductor and charge conductor and magnetic field is applied, right? In that case, across the faces of the conductor, EMF will be generated. So the moment we change B, this EMF will change. So in Hall effect type of flow meters, in the rotor, in the vanes, a magnet is fixed. In the rotor, a magnet is fixed, and when the magnet moves with the rotor, the magnetic field associated with the rotor is changed. Here there is a sensor, right? And electricity is passed through this sensor, and due to this magnetic effect, the EMF this sensor is measured. So this is the basic principle of the working of the Hall effect flow meter. So there is another flow meter which is known as thermal mass flow rate meter. Now thermal mass flow meter, we can have different type of arrangements. One arrangement is Q is equal to mCp delta T. This Q is heat transfer, Q, right? Q is equal to mCp delta T. Now if we have Cp for the fluid is known, if we know the delta T and Q is the heating of the fluid, we can find the mass flow rate. This is the working principle. Now this working principle is slightly modified, or we can develop a flow meter based on this principle also. Q is equal to mCp delta T. So in a tube, heating is done, Q. This is T1, this is T2, right? So what is the temperature rise in the tube, right? This temperature rise multiplied by the specific heat, Cp, and Q is equal to mCp delta T. So m is equal to Q by Cp delta T. That is one thing. Second thing, in a tube, 2 electrodes are put. There are 2 electrodes, right? They are not, I mean, one after another. They are side by side. They have been put. So it is. The figure is something like this. Right? Now, fluid flows over these electrodes. Let us say one electrode is at temperature of the water, let us say 25 degrees centigrade. Whatever the temperature of water is, it will acquire the same temperature of water. And this electrode is heated, and some energy is given, electrical energy is given, and it is heated, and temperature difference of 10 degrees centigrade is maintained. Now, in order to maintain this temperature difference, electrical energy input has to be given to, let us say, electrode A and electrode B. So, for electrode A, electric energy input has to be given. When the fluid flows over the electrode, it will take away the heat, temperature will tend to go down. But we have a feedback control mechanism. So, the energy transmitted to this electrode will further increase, or vice versa. If we decrease the velocity, then energy transmitted to this electrode will decrease in order to maintain the temperature difference 10 degrees centigrade. Now, we can relate the velocity of the fluid with the energy supplied to the electrode, and this energy supplied to the electrode is a function of velocity of the fluid. And this is how we can find the velocity of the fluid in the thermos mass flow rate meter. This is all for today. From the next class, we will start with the temperature measurement. Thank you.